So the primary textbook that I will use for the course is the book by Nielsen and Chuang. It's just called Quantum Computation and Quantum Information. It's Cambridge University Press. The first edition is, I think, 2000. They have an updated edition, which is 2010. Okay. And I'm sure there are several soft copies of this floating around. Please ask around. Please ask your seniors. Somebody will have a soft copy of this book. Okay. The other resource is online lecture notes by John Preskill. At Caltech. Okay, so you Google this, whatever I write down here, and you'll get the lecture notes. These are the two main textbooks that I will use. Other online resources. So on YouTube, you have lecture videos by Preskill. So his entire course, he has recorded lectures. I encourage you to go watch them. I should warn you that the course will be structured differently, right? I don't structure the course the way he structures it. So you'll have to look for the appropriate videos to watch when I'm covering that material, right? The material will not be covered in the same order, okay? And there are also linear algebra videos, lectures. This is a classic, actually, linear algebra lectures by Gilbert Strang, I think. It's again MIT. And I think his lecture notes are also available. Okay. As far as I know, this is one of the simplest resources for linear algebra. Okay. And if there are students here who want to share other resources that they come across, please feel free to share with the class. You can post it on the chat, right? As far as the linear algebra background is concerned, I would simply also recommend chapter 2 of this Nielsen and Chuang book. Okay. Because chapter 2 basically covers all the background that you need for this course. Okay. It covers both linear algebra and quantum mechanics. And the linear algebra is it's a very succinct description of what you need exactly for this course, right? Which is finite dimensional linear vector spaces. So it gives you a succinct description of what you need. So I would encourage you to go through chapter 2 of Nielsen Chuang. Okay. And I myself will also point you to certain sections as and when I cover them, right? Okay, so I wanted to make today's lecture a kind of curtain raiser. That's what I've titled this. So before, I didn't want to just start off by telling you about, sort of getting all technical in the very first lecture, but I wanted to give you a glimpse of what this is about, right? So sort of theme of this course is basically, or you can say the slogan, if you will, for this course, is this quote by Rolf Landauer, which I really like and which I often quote, which is that, information is physical, right? So this is Rolf Landauer, in many ways one of the pioneers of this field, although people don't often recognize his contributions here. Was at IBM research. So what does this mean, right? So the idea is that when we talk about information, whether information storage, information transmission, computing, etc., right? Information processing, right? Then this cannot just be a mathematical description, right? It is the nature of this information changes fundamentally depending on what kind of physical systems you invoke in performing all these tasks, right? And so when you, what the kind of information processing that most of you know and are aware of is processing using, so we're going to start calling them classical bits from now on, right? Because this course is all about quantum bits. Most of us kind of know and understand what kind of objects classical bits are. And we have worked out an entire scheme by which we can store, transmit, communicate, compute, do whatever we want using classical bits. But now the question becomes, what happens if your bits become truly quantum objects, right? Then how does the nature of this information change, right? And that's what Landauer's quote is hinting at, that it's not just about, it's not a given, that everything you know and observe based on classical bits is going to go through once you start talking about quantum bits. In fact, we'll find several counterintuitive things happening. Things that are very easy in the classical case actually become impossible in the quantum case, right? So let me say that upfront. It's not that every task that you can do using classical bits becomes easy using quantum bits, right? And the prime example of this, such a task, is, of course, the copying, right? The ease with which you can copy classical information, you simply cannot copy quantum information, right? So you have tasks like copying, which are extremely trivial in the classical case, which actually become no-go theorems in the quantum case. But on the other hand, there are tasks which are extremely hard in the classical case, which become extremely simple in the quantum case, right? So what are classical bits? Classical bit is simply a binary valued object, right? It's an object that takes value in a binary field, right? So let's, I mean, of course, you can have higher dimensional alphabets and so on, but let's, for the purpose of this lecture, just stick to a binary valued symbol. So that's a bit, that's a classical bit, right? And we know and understand how to manipulate them, store them, etc. Now, what is a quantum bit? Now, a quantum bit or a qubit, just an interesting nugget here, that the word quantum bit was actually coined by a physicist called Ben Schumacher in 1995. Okay, he coined the term qubit to refer to quantum bits. So the idea is that now you are going to associate a vector space with this set. That is one way to think about it. That in place of 0 and 1, which are just two objects in a set, right? I'm going to think of a space that is spanned. I'll come to what I mean by spanned, right? By two objects, which I will denote like this, okay? So this is what is called a ket, okay? So when I put the 0 inside this vertical line and this right angle bracket, this is what I call a ket, okay? So this will be called ket 0, and this will be called ket 1. I'm really sorry about the background noise, guys. We have some work going on and not able to get to office either. I hope the noise is not too bad. Yeah. You guys can still hear me all right?
Yes, ma'am, it's fine. Yeah, there is no disturbance we are hearing.
Okay, great. Thanks. All right. So corresponding to the classical 0 and the classical 1, okay, I'm going to associate a ket 0 and a ket 1. And this ket symbol is not just to distinguish the fact that I'm talking about a quantum bit. It really is telling me something else. It's a notation to tell me that these are now vectors in a vector space. Okay. So what does that entail? If I have two vectors in a vector space, then I know that any linear combination, so let me be precise and say that these are vectors in a linear vector space. Okay. okay, which is important. The linearity is very crucial for us, right? So I can now take linear combinations, okay, of the form alpha 0 plus beta 1. Now, let me qualify this even further, because those of you who know a little bit of linear vector spaces will immediately ask me, what field, over what field are you constructing this vector space? So I'm constructing this over the complex field. So these are now vectors in a complex linear vector space, okay? So I can take complex linear combinations of the form alpha 0 plus beta 1, and this would also be a valid state of the qubit, right? So by moving away from this mathematical description, which is that of simply a binary field, the classical bit can exist in one of two values, can take on one of two values, 0 or 1. It's like a binary value random variable, right? I have now introducing the idea that I can have a quantum bit which is represented by two states, ket 0 and ket 1, okay? But the description doesn't stop there. It is not that the quantum bit can exist only in the 0 state or the 1 state, but the quantum bit actually lives in a linear vector space, and a space that is spanned. And this is what I mean by span, right? I mean that any linear combination of these two objects is also a valid element of this space, right? This is a space which is comprised of linear combinations of 0 and 1. So I now have an object which is not binary valued, but it's actually a vector in a two-dimensional vector space, okay? So a qubit is therefore, I will often use this term span, okay, to denote that I'm taking linear combinations of two or whatever number of basic vectors, okay? So it is a span of these two vectors, and the precise mathematical way of saying this is that this is an object that belongs. So this is, for those of you who, this is the belongs to sign, okay? And I'll often use this also. So I hope you, yeah, I should mention that. So this is the belongs to symbol. It belongs to what we will refer to as C2, right? And what is C2? It's a two-dimensional complex linear vector space. So we'll get into further details of this as we proceed in the course. But for now, I only want to remark about this fact that the qubit now has available to it, rather it can explore not just these two states 0 and 1, but it can explore a whole continuum of states of the form alpha 0 plus beta 1, where alpha and beta are complex numbers. C just denotes complex field. C2 will denote two-dimensional complex linear vector space, right? One concrete way to visualize this, okay, two concrete ways, right? One mathematical and one physical, okay? Physically, how can we visualize this? Well, think of polarization states of light. This is something most of us must be familiar with, even from just high school physics, right? So you know that light is a transverse electromagnetic wave, okay? What this means is if I have a certain direction of propagation, right? Which let me call this as, actually let me call this Y, okay? So this is the y-axis for me, and the light is propagating along the positive y-axis. Then I know that the electric and magnetic fields whose oscillations constitute this electromagnetic wave, they have to be oscillating in a plane that is perpendicular to the direction of propagation, right? That's what it means to say that it's a transverse wave. So this is the xz plane, right? And the polarization vector, which could be the electric or the magnetic field, let me just call this a P vector for now. This polarization vector must exist in the xz plane. Now this plane is described by exactly two perpendicular directions, right? The X and the Z. So I can think of X polarization as so-called horizontal polarization. Okay, and in my notation, I will associate a ket with it. Okay, I will call this the ket vector associated with horizontal polarization. The Z polarization, I can think of this as vertical polarized light, and I will associate a ket V with this. Okay, and so this constitutes a qubit for me, right? So this is a qubit. It simply is the span of these two states, right? The horizontal and the vertical polarized light, because I know that I can take any linear combination of this and get another polarization vector in the same plane, right? So once I fix a certain direction of propagation, here I've said that the y is my direction of propagation, then there is a certain plane in which this polarization can exist, and it is spanned by exactly two perpendicular directions. So this terminology of so-called perpendicular directions, in this case, will sort of translate to orthogonal vectors or orthogonal states in the vector space. I'm making a very loose association now. This will be formalized in subsequent lectures, but this idea of orthogonal vectors becomes very important here. So this H is what I can refer to as ket 0. For example, this is 0 state of my qubit. The V, I can think of this as a 1 state of my qubit. And in fact, this polarization qubit was one of the first physical realizations of a quantum bit. One of the earliest quantum protocols, namely quantum key distribution, was actually implemented using the polarization qubit in the early 90s in IBM, in the IBM lab in Yorktown Heights, right? So this is a simple physical example of what I'm talking about, that you have two different states of a system, which can be thought of as the 0 and the 1, but the physics of the system, the physical properties of the system allow you to make states which are linear combinations of 0 and 1. So what kind of linear combinations can you think of now? You can have, you have the horizontal and the vertical. So let me try to use some other color maybe. So I have these two, right, which I have made as my basic 0 and 1. But now I can construct, for example, these kind of polarizations, right? I can make, let's say, 45 and 135-degree polarized, right? These are also often called cross polarizations, or you can think of left and right circularly polarized, which are all linear combinations of the X and Z, right? So yeah, this 135 is not, excuse my drawing, but I'm basically trying to say that you have something in the XZ plane itself, okay? Right. So this is one physical visualization of the qubit. There are more which we will discuss as we go along. Mathematically, how do I visualize the qubit? How do this ket 0 and ket 1 is just some abstract notation, right? So how can I make this more concrete, right? And the way to make it more concrete is using a matrix representation for this. Okay. So mathematically, I will make the qubit description more concrete by introducing a matrix representation. So what does this matrix representation mean? I have this ket 0. I said it belongs to a two-dimensional vector space. So I will associate with it what I call a column vector. This is basically a 2x1 matrix, right? It's a matrix with one column and two rows, right? It's a 2x1 matrix. And what are these two entries? So since ket 0 and ket 1 are going to be my basic analog of the classical bit value 0 and 1, I'm going to populate these entries as 1 and 0. And I'm going to refer to ket1 as the 2-column, so this is called a 2-column vector, right? Column vector with 2 entries, 0 and 1. Was there a question? Okay, so this is one way to represent this abstract idea of the 0 ket and the 1 ket. Okay, and now you see that an arbitrary, general qubit state, we said it can exist as a combination, right? So a general qubit state, and I will introduce the notation psi now. So this is what we call ket psi, right? This, as we said, can be written as, yes, I did start.
I think you've started the recording, ma'am. It shows it here.
Yeah, it is recording, right? Okay, so alpha 0 plus beta 1. So this, the technical term for these kind of linear combinations, at least in the physics parlance, we will refer to this as a superposition, right? This is what we will call a superposition of 0 and 1, okay? How would I represent this in this matrix notation? So this will become alpha times this column vector 1, 0 plus beta times 0, 1. So this will simply become the column vector alpha beta. And so I can simply represent all my qubit states in terms of column vectors like this, right? So what have we done so far? We have tried to contrast the classical bit from a quantum bit, right? And we simply said for now that a quantum bit is something that exists in a vector space as opposed to a binary field. It's something that exists in a two-dimensional vector space where you have associated a ket 0 with the classical 0, a ket 1 with the classical 1, and the fact that they belong to a vector space immediately gives us this idea of linear combinations or superpositions. And so I can take arbitrary combinations of 0 and 1, and this is a valid state for the quantum bit to exist in. And we've seen two ways of visualizing this. Physically, this kind of a structure, this kind of a mathematical structure naturally arises in several contexts, of course, right? That's what, when we introduce quantum mechanics, we'll see that. But it naturally arises even in the context of something like polarization states of light. And this is something we are all familiar with, so it's a good example to often think about this in terms of polarization states of light, where you have this idea that you have two distinct states and all other states become combinations of linear combinations or superpositions of these two states. Mathematically, these abstract kets that one writes down can concretely be visualized as column vectors. Okay, so the first departure from classicality, right, based on whatever description I've given you so far, is the idea of superposition, right? So the fact that your qubit can now exist in states like this, right, which I simply call psi, right, means that the qubit can now explore a lot more, has a lot more space to explore than a classical bit. Okay, so I'm introducing the term Hilbert space here, which I will formally define in one of the subsequent lectures. But the idea is that the state space of a qubit, which one can technically call a Hilbert space, gives the qubit a lot more room to play around with, right? So this is a nice quotation by Carlton Caves, who says that Hilbert space is a big space, okay? But now that you've created this object, or you have thought of this object, which is a, vector as opposed to just a classical binary variable, how do you think of computing with this? right? What does computing with this kind of an object mean? So the question becomes, how do you transform qubit states, right? So you know how to compute with classical bits. So classically, you have your the so-called logic gates. Was there a question?
Yeah, ma'am, I have a question.
Yeah.
Ma'am, so when you describe that physical realization of qubit, right, using the polarization states of time, there, I mean, in a way, if we talk XZ plane, it is in a real Euclidean plane, and the superposition that there would be possible are, real over the real field. However, when we are defining, a general qubit, we are taking complex superposition. So my question was that, this polarization qubit that we have taken, in a way, the number of states, or number of room, in a way, if I say that in a layman term, that is available to the qubit, number of realization would be less than what theoretically it is possible, right? In a way.
Yeah, but I should tell you that it is a misunderstanding to say that, well, okay, so let me address this question in two ways, the two aspects to this. First of all, what if I have only real superpositions, right? What if I allow only real valued superpositions? Or if I say that my alpha, beta in this description have to be real, right? Then, so this is an idea which has been explored by people. So if alpha, beta have to be real, okay, then this idea is what is called a rebit, okay, or a real qubit, so to speak. Yeah, a rebit, okay, let's say. There are papers by William Wouters, okay. So for those of you who are interested, you can go and explore. So it turns out that, of course, you cannot do half as much as you can do with a qubit. In fact, certain things that you can do, certain properties fail, then you're allowed only these kind of real superpositions. However, and okay, so let me also tell you that the task for which these polarization qubits were used involved only real superpositions, real combinations, okay? So for example, this 45-135 that I described, so the 45-degree polarization can simply be thought of as 0 plus a combination of 0 and 1 with equal superposition coefficients or equal alpha and beta of 1 over root 2. Similarly, the 135 can be thought of as 0 minus 1 by root 2, right? So these are all real coefficients, right? 1 by root 2, 1 by root 2, 1 by root 2 minus 1 by root 2. Turns out that this was sufficient to actually demonstrate something called quantum key distribution, okay? However, if I truly write down the mathematics of the polarization vector, then it is indeed a vector in a two-dimensional complex linear vector space. Okay, so we can actually work out a problem based on this, or I can tell you exactly how. The point is, of course, you have to bring in the phase, right? There is a phase that you associate with the electromagnetic wave. And so when you make these superpositions, you are indeed allowed to make complex superpositions. Okay, so it is not true that if I use a polarization qubit, I can only make real superpositions. I can indeed make complex superpositions. And the physics of it very much allows these complex phases and superpositions, right? So yeah, that's the answer to your question. Yeah. Okay. Okay, so I was going to talk about how do you compute with this kind of objects, these quantum bits. So classically, everyone is familiar with logic gates. More mathematically, these are what I would call Boolean functions, right? They are functions that map 0, 1 to 0, 1. Or they can map several bits to a single bit, right? So I can have single bit gates. Okay. So what is a single bit gate classically? It's a mapping from 0, 1 to 0, 1. Now there are very few single bit gates in the classical case, right? What are the single bit gates? that you guys know of?
Only two, not and oh,
Not,
not
yes,
not
and
it. And nothing, just pass it as it is.
identity.
Identity.
So that's what I would call the identity gate. Okay. So the NOT gate does the following, right? It flips 0 to 1. And so let me write it like this. So if I were to pictorially depict the input output, it takes 0 to 1 and 1 to 0, right? And of course, the identity gate simply takes 0 to 0 and 1 to 1. And these are the only two single bit gates or single bit Boolean functions, right? And then you have multi-bit gates, what I will call multi-bit gates, okay? Because I'm going to talk about multi-qubit gates shortly. And these are typically these have two inputs and one output in the classical case, right? Those are the kind of basic building blocks of your classical circuits. So what are these? Of course, everyone knows these. You have the, so I would write them as 0, 1 cross 2, right? Because that's a 2-bit input and maps it to a single bit output, right? So that's a 2-bit, the input is now a 2-bit register and the output is a single bit, right? And of course, you have this whole set of them, which everyone here is hopefully familiar with. I don't think I've left out anything. The crucial thing is this idea of universality. So can someone tell me what is universality in the classical case? So if I'm doing classical computing, these are all the gates I need to know, right? But of course, my computer is realizing much more complex operations. So what is universality?
Ma'am, it's like having a basic set of gates using which we can design some complex circuits.
Okay, exactly. So thank you. So any Boolean function can be realized using a basic set of gates. Actually, in the classical case, you just need a single gate, right? So can people tell me examples of these? So there are these so-called universal gates.
Then not.
Exactly. So in fact, in the classical case, you have a single gate, which is the NAND operation or the NOR operation, using which you can realize any Boolean function, right? So now the question is, how does all of this translate to the qubit case? Okay, so let's look at the quantum analogs of all of this. So the first aspect was what are gates in the quantum case? Okay, gates are transformations of this two-dimensional complex vector, right? So what kind of objects do you think quantum gates will be? So I have to, for example, transform. So what would be a, so let's try to design a quantum NOT gate. Okay, and maybe I'll stop today's lecture with this. So what would be a quantum NOT gate? Let's look at the simplest example of a single qubit gate. What does it have to do? It has to transform 0 to 1 and 1 to 0, right? And what is 0 for me? That's why it's useful to have this mathematical representation. What is the 0? It's this column vector, right? 1, 0. By the way, you should realize that there's nothing sacrosanct about associating this particular column vector with get 0. That's a canonical association, that's all. I could have, instead of this, tried to write down 0 as 1, 1 or something, you know. Yeah, basically it's just an association. So, okay, so now I have to somehow transform 1, 0 to 0, 1, right? That's how I represented my ket 1. the quantum bit 1 is 0, 1. The quantum bit 0 was 1, 0. Okay. So what kind of mathematical object would do this transformation for me?
Linear matrix.
Exactly. So it has to be the so-called linear transformations or linear operators which are nothing but, in this representation, they are matrices. And to be precise, I have to transform a 2 cross 1 matrix into another 2 cross 1 matrix. So note that I will call these as vectors, right, in my language, because essentially they just have one column, right? So I will call them as vectors or column vectors, but in effect, they are 2 cross 1 matrices, right, in this matrix notation. So what kind of matrix do I need to do this transformation?
Ma'am, a column vector
cross
with
two.
-1 and 1 as entries, we can add.
Anti-diagonal matrix.
But what is the dimension of the matrix? That's what I want to know.
2 cross 2.
Ma'am, 2
Okay.
cross 2.
Exactly. Yeah. So I need, and yeah, you're indeed right that you need an anti-diagonal. So a 2 cross 2 matrix acting on this. And when I say acting on this, I mean a matrix product. Okay. I think someone had the idea that I could add something to this, right? But that is not how you would transform vectors, right? There's a linear transformation that has to act on the vector, right? So what one's talking about is a matrix product like this. And what kind of matrix would do this? Indeed, there has to be a matrix whose diagonal entries are 0 and the off diagonal entries have to be 1. So please check this, right? That this indeed achieves this transformation. So what I have written out for you is indeed the quantum NOT gate. This is often called the X gate. Okay. We'll see why when we discuss the physics of this. And this is simply this 2 by 2 matrix 0, 1, 1, 0. So I have shown you that this transforms. So the way I would represent this in an abstract way is to say X acting on ket 0 gives me ket 1. So it's up to you to check that X acting on ket 1 gives me ket 0. And I will also describe this for you as a circuit. So here's a simple quantum circuit where I take, so the gate, the logic operation is described like this with a box with an X in it, right? And the input is 0, the output is 1. This I have shown for you, okay? This is just this matrix equation. It's up to you to check if the input is 1, the output is 0, okay? And since we are almost at time, let me stop here, but leave you with this question. So this is the homework for you. So if the input to the X gate is 0 plus 1 by root 2, okay, is it this kind of a state? What is the output? Okay, so this is something you can work out for me by Thursday's class. Okay, also to give you some familiarity with working with objects like this, how do you think about this question also, right? And work this out. So what I'm asking you is to evaluate the output of this simple quantum circuit. I have X, I have the input, which is 0 plus 1 by root 2. So what is the output? Okay. Okay, so let me stop here. I will continue on this theme for the next lecture where I want to show you. So the whole idea is this, right? Instead of giving inputs 0 and 1, which is all that is possible in the classical case, I can now do this, right? What I'm asking you to evaluate as homework, I can now give inputs which are superpositions. of 0 and 1 and evaluate the output. And it does not cost me anything more to evaluate the output for the superposition state. It does not, for example, require 2 evaluations of the X gate, right? I apply the X gate once and I can input either the basic 0 or the 1, or I can input any arbitrary superposition, right? And you already see this idea that you can, in some sense, simultaneously evaluate different or the values corresponding to different distinct states like 0 and 1 without having to implement the gate multiple times. So what I will talk about more next time is this idea of quantum parallelism. Okay. Okay, so let me stop here. Any questions?
So ma'am, when I say input a state vector v to this gate x, it so when it's being inputted, it doesn't really have a single value. So what you said was it has all possible combinations of these ket 0 and ket 1, and the gate will compute for all of them, but only when we want to find the exact value, it will take on some value particular state.
Yeah, so what you're asking me is what happens next, right? So let's say I evaluate the X operation on the superposition, but how does that tell me? For example, if I still want to know what is X acting on 0 or X acting on 1, I still have to, so what I need to do then is what is called a measurement, right? So I will have to measure the qubit, and indeed when I measure the qubit, I will have to collapse the superposition, right? That's what the quantum measurement postulate says. For those of you who know a little bit of quantum mechanics, the measurement postulate tells me that I will have to, the superposition, it collapses down to one of these distinct states. Like this path, what I'll show you next class with a simple example of how you can cleverly use this parallelism. Despite the fact that you have to measure at the end and measurement collapses the state, you can still make use of the fact that you can input superpositions, you can evaluate superpositions, you can extract useful information from this, right? We'll see this next week. But indeed, this is a challenge, right? This is why it's not an easy breeze, right? Oh, we have superposition, we have a lot more room, so now everything is just exponentially faster. No, everything is not exponentially faster. A lot of work has to go into designing algorithms, designing techniques by which you can still measure at the end and extract information in a way that exploits the superposition principle. Okay?
Yes, ma'am.
Yeah. Any other questions? Okay, so there are no more questions, then I think we can stop today's lecture here, and I'll meet you all on Thursday morning at 10. Somebody has already evaluated the answer. Yes, you are right. Whoever flashed the answer, that is correct. Stop the recording.